All right, welcome back. We're going to add in a couple more concepts here. Power and efficiency. So given work, power is work over time. Okay? So power is defined as the derivative of work with respect to time. And so given our previous definition of differential work, if we divide by dt, dr dt, well, that just gives us, if force is constant, we have force inner product with velocity. So you've seen that before. Efficiency. It's simply power out over power in. Should always be less than 100%. All right, so our first problem we're going to consider is we have a pulley problem. So here's our ceiling up here. And so we have a cord hooked in here. Come straight down. We have a pulley here. And we're going to neglect pulley and cable mass. And that comes up, goes around another pulley, and it goes here. And here's a motor with a spool that's gathering up all the rope. Okay? And so we're going to be told this is going to start from rest. And when it gets to 4 seconds, it'll have gone through constant acceleration. But at 4 seconds, the velocity going up is 10 feet per second. So that's what's happening at 4 seconds. But somebody says, well, that's nice, but I'd like to know what's the power in, given all this information, at 2 seconds, a different time. Well, that's kind of inconvenient. Well, so let's think what we have to do. So let's just kind of figure out what's the goal. All right. The power put into the rope is going to be what? It's going to basically be force times velocity. There's going to be a force in the rope, that's tension. So we got tension in the rope, and the velocity is going in the same direction, so that's a positive concept. So force times velocity, or tension times velocity, that's going to be the power output over here. And once we know that, then divide by 0.76, we'd have the power input needed. All right, so we need to get the tension in the rope. To get the tension in the rope, well, let's think. Where can we get that? Well, at some point, if we were to sum the forces along here, we could get the tension versus the crate and the acceleration coming up. So if we want the tension, if we know the acceleration here, we could use Newton's law to get acceleration. That'll give us tension. So I'm just looking at what we're going to need and going backwards and thinking. Okay. What else are we going to need? So we need acceleration. Well, we know the velocity at 4 seconds. We need to know the velocity that this is moving up at 2 seconds. Okay, so knowing constant acceleration, we're going to be able to get that. So that would give us the velocity coming up here, but we have a pulley system. The speed of the rope is going to be different than the speed of the box. So those are the problems we have to deal with. All right. So let's just deal with the box by itself first. That's, I think, the easiest thing to contemplate. All right. So I have this box, okay, and it's going to start with velocity is 0, and it's going to go up for 4 seconds, where velocity gets to 10 feet per second. And it's constant acceleration. All right, so we have V1 is V0 plus AT. You've all seen that a million times. So 10 equals 0 plus acceleration times 4 seconds. Acceleration is simply 2.5 units R, I'm still in pounds, feet per second squared. Okay? So we got that. Well, then knowing that, well, this is really easy. The question is we need to know the power in at 2 seconds. So I need to know the power of the box, the velocity of the box at 2 seconds. Then I can get the velocity of the rope, and I'd have that V term that I need. All right? So V equals 0 plus A times 2. Well, we know that. So 0 plus 2.5 times 2 equals 5 feet per second at t equals 2. So I know the speed of the box when t equals 2. Well, what's the speed of the rope? Okay. Well, to get the speed of the cable, I'm getting a little low here. Go on up. Speed of cable. Let's figure that out. Okay. Now what you should have, what you want to recall is when you deal with a pulley, the key is that we assume the rope does not stretch. Whether it's a chain, it does not shrink. So the idea is to come up with an equation like so. So let's just, we'll come up with a coordinate system where from this point down to that point, or equivalently from here down to there, I'll measure down from here to the center of this pulley. I'll call that D1. And then I'm going to measure as rope is pulled off from the center of this pulley going this way, D2. So as I'm pulling rope along, let's think where it's going to go. As I go down from here, this distance will change, but the distance around the pulley is constant, so I can ignore it. It's always the same. Then this distance equals that distance. This distance around the pulley is also the same, this quarter turn, so we can ignore it. And then we have this D2. So here's what we have. This plus this, so 2D1, and I'm measuring that positive down at the moment, plus this distance coming off here too, equals a constant. Why is that useful? I can take the derivative. So I'll call this 2 d1 dot plus d2 dot equals 0. Okay, so that tells me what I'd like to know is this d2. That's the critical one. Well, d2 equals minus 2 d1 dot. Okay, well, at 2 seconds, this is coming up at 5 feet per second, but here I'm measuring positive down. So I have minus 2 times minus 5 equals 10 feet per second. So at 2 seconds, this is coming up at 5 feet per second, and we're drawing rope off at 10 feet per second. So I need force times velocity to know the power output. I got the velocity. Well, now I need the force. Okay. Well, force, I know the acceleration. Force and acceleration, that's screaming Newton's law at me. So let's apply Newton's law. I've got a 50-pound crate. There's gravity, 50 pounds. So if I look up here, oops, let's get that in. So the pulley's massless, rope's coming off, and I have a tension and a tension. There's 2 tensions there. So that's telling me 2t minus 50 pounds. And you want to know something? When people go to solve for the tension, I'm going to tell you the mistake almost everybody does. They come here and they say that's equal to 0, and they say t is 25 pounds, and then they add that in here, and bam, you just lost half the credit on the problem. No. It's sum of the forces equals ma. You got to remember to put this in. 50 on 32.2, acceleration is 2.5. Okay, now you solve, and you come up with t is 26.94 pounds. All right. Well, knowing that, we have the power in the cable is simply 26.94 pounds times, what was the pounds, and 10 feet per second. And so we have 269.4 foot-pounds per second. Or pound-foot per second, whatever you care to write. No big deal. Okay, so how much power is required? Input. Well, we have 76% efficiency. Power in is simply 269.4 divided by 0.76. which is 354.49 foot-pound per second. Bring that up. Now, if you note that 1 horsepower is 550 foot-pound per second, that means, bringing this number down, PN required 0.64 horsepower. So, that puts our efficiency and power to use. Fairly straightforward. Let's move on to our next problem. Where did I put it? Here we go. So here's our next problem right here. So I have a box, 25 kilograms, so moving into the SI units. There's friction. So UK is 0.4. And there's a box providing a tension in the line. So it's a 500 Newton tension. So I'm not looking at the torque of the motor, just the tension here, pulling this along. So that's 500 Newtons. And what I want to find is the velocity after a 5-second slide. Okay, so 5 meter slide, excuse me, after a 5 meter slide. So here we have velocity and distance. And whenever you see velocity and distance related, it's guaranteed to be an energy problem. And once I'm done, we want to figure out what the acceleration is. All right, so here's the free body diagram. So we have, here's our 500 Newton force. Tension in the cord. Here's our weight. Normal force pushing back up, and then that creates the friction here, 0.4 times the normal force. And this is obviously a little confusing because this end refers to normal force, that end refers to the unit of newtons. Okay, it's a little nutty. Anyway, so we have 0.4 times the normal force. That's what those two are supposed to be. Gives us 98.1 newtons. A few too many ends, but it's easy enough to follow. Okay, so the first question, what is the velocity after a 5 meter slide? So this thing moves along 5 meters, what's its velocity? Okay, that's an energy problem. T1 plus V1 plus work 1 to 2 non-conservative equals T2 plus V2. So initial kinetic and potential energy plus the non-conservative work going from state 1 to state 2 is the second kinetic energy plus potential energy. All right, we're told it starts from rest. Goodbye. We'll deal with ground as being 0, so no change in height, 0. By the same token, no change in height, V2 is 0. Non-conservative work. Okay, there are two things doing non-conservative work here. We have a motor, we have friction. All right, we have a motor going one way, that'll produce positive work, minus the 98.1, the friction, going the other way, going through a distance of 5 meters. Okay, this number here is, let's see, 401.9 equals, okay, kinetic energy. 1/2, let's see, we've got 25 kilogram box, so 25 for M, V squared, solve for V, get 12.68 meters per second. All right, so we have that. So we did that. What's the acceleration? Oh, well, that's easy enough. Sum of the forces in the Y. Or the X, rather. Taking the X along here. So, let's see, we'd have 500 minus 98.1, which is 401.9. Let's see. That must equal, see, sum of forces equals MA. 25 times acceleration. Okay, solve for acceleration. I must have the number here somewhere. 16.076 meters per second squared. So, we've had our first problem dealing with non-conservative work. Very straightforward. People usually don't have much trouble with that. The next set of problems we're going to look at, we're going to start having multiple masses. So here this was just one mass. We're going to start allowing there to be multiple masses. When that happens, it's really no big deal. So you would simply say T at state 1 would be 1/2, say mass 1. I'll call it mass A. Mass VA1 squared plus 1/2. If there's another mass, call it mass B, VB1 squared. And just add them all up. No big deal. Initial kinetic potential energy would be mass of A. G is the same for all of them. Let's call it HA, initial state, plus MB, G, H, and its state, like so. Very straightforward. Just for every mass, add them all up. Not a lot else to say. Catch you in a bit.